All right, so now we're going to talk about the connecting homomorphism. Okay, and I'm going to put in this corner, it's like the spaces we're going to work with. Okay, so VP plus 1 to WP plus 1, right? And then VP, WP, UP here. UP minus 1, VP minus 1, WP minus 1. And then UP minus 2, VP minus 2. Okay, and I'm going to label these boxes corresponding to commutative blocks because we're going to refer to them in the proof. So this is 0, 1, 2, and 3. All right, so we're going to put this in the corner here, all right, and so we're oftentimes going to suppress it's like some of the subscripts just to sort of make this a little bit sort of less onerous. Okay, so we've labeled right the commutative blocks. In the diagram. All right, so because we're going to refer to them. Okay, so let's define this in several steps. So I'm going to choose a gamma. So essentially what I'm going to do is that I'm going to snake from a generator, it's like of homology, it's like in WP, it's like back to something in UP minus 1. Okay, so so let's just think of it this way. So I start with alpha. Okay, so we start with alpha, which is in WP. Okay, and it should be a cycle because it's a generator of homology. So there's a cycle representing a class in HPW. All right. Okay. So we're starting at alpha, right? So this thing across is exact. So in particular, this means that this map here, right, which is psi, is surjective, right? So psi is surjective. So that means there exists some element beta in VP such that psi of beta is equal to alpha. Okay, so let's write that down, beta. Okay, so we know that alpha is a cycle. So that means that the boundary of it is 0. So this is W, right? Maps to 0. So that means that W of alpha is equal to 0. Okay, and then of course what you're going to do is you're going to use the fact that this diagram commutes. Okay. So this is the diagram corresponding to 0. Right, so hopefully you see where we are. Alpha is in WP, beta is in VP. Alpha in WP maps to 0 in WP minus 1 via the boundary because alpha is a cycle. Okay. Okay, and so we need to have something here, right? So I'm sorry, this of course clearly maps to V of beta. Okay, so by this block commuting, right, that means that the boundary of beta, which is V beta, right, maps by the commuting, by the chain map, it's like to 0. Okay, so by this and the exactness, actually by, let me just say by this commuting, that means that, so these are the phi's and these are the psi's, right? Psi of V, well, let me just write psi V of beta, psi V beta, right, is equal to 0. Okay, so that means that V of beta is in the kernel of psi, right? But this is equal to the image of phi by exactness at V p minus 1. Okay. All right, so V beta is here. This maps to 0. So V beta is in the kernel. It's like of this map, but it has to be in the image of this map by exactness. All right. So this means that there exists now something else. Let's call that gamma, right, which maps by phi to Vb. Okay, so it exists gamma in U p minus 1 such that the image of gamma is equal to V of beta. Okay, so that now is the candidate generator of a homology class in, it's like p minus 1 dimensions on U. Okay, so we start with a cycle representing a homology class on dimension p. It's like on W, and we mapped it to something here. All right, so that's the candidate for generating this connecting homomorphism. And then what remains to show is that, well, actually, we're not quite done yet, right? Because, so this is just now just a chain. We have to show that it is indeed a cycle. So the first thing you need to show is that this is indeed a cycle. And then we need to also show additional two things, right? Because I have a choice in alpha and I have a choice in beta. So I need to show that it's independent of those two choices as well. So what remains to show is that gamma is a cycle, and at the level of homology, the map, this connecting homomorphism is independent of the choice of alpha and beta. Okay. All right. So this is what we have so far. Okay. All right. So let's try to show that first gamma is a cycle. Okay, so step 2, show gamma is a cycle. Okay, so what we're going to do is we're going to have to fill in, it's like this part of the diagram. Okay, so we know that this is a chain complex. So what that means is that beta maps to v beta, which maps to v squared beta, right? But v squared is always 0, so this maps to 0, right? So since v squared is equal to 0, right, that means that v of beta is equal to 0, right? Then of course it's like you use the fact that the diagram commutes, right? So this is u, this is phi. So this is principal something. Okay, so let's just leave that for a second. Okay, so this is 1. Okay, so, and then 1 commutes, which means that u of gamma with psi of u of gamma is equal to 0. But you can use the fact that you have exactness at up minus 1, actually, sorry, at up minus 2. So exactness at up minus 2 implies that phi is injective. Right? So that means that you know, it's not just that phi of u of gamma is equal to 0, but that u of gamma is 0, right? Which implies that u of gamma is equal to 0, which is exactly what you want, that gamma, when you act upon it by the appropriate boundary operator, is 0, right? So it implies that gamma is a cycle. Okay, so in any case, it's like what you see then is that, so this actually maps to 0 here. Okay, so this is where we are right now. And you see it's like, this is called the zigzag lemma because you go from alpha to beta to via beta back to gamma, right? So this is called the snake or zigzag lemma because we snake through the diagram, right? Or zigzag through the diagram. Right, so we go from alpha to beta to v beta to gamma. Okay. All right. Anyway, so we've showed it's like a candidate gamma. We showed that gamma actually is a cycle, so it can potentially be a generator. It's like of a homology class. Okay. So gamma is a cycle. So it is a generator of a class in HP minus 1U, right? Which is what we want. Okay. So now again we have to show that this class doesn't depend on the choice of alpha and beta. Okay. So this is step 3. So we're going to show independence of the choice of beta first. Okay. So the way we're going to do this is that we're going to assume that there's some other beta which you could have chosen. All right, and then see what happens. So let me try to do this. So let's say I have a beta 0 here, right? And then you get a v of beta 0, and then you have a gamma 0 here, right? So we're going to track that. We're going to show essentially that the difference between gamma and gamma 0 is a boundary, and if it is, then that means that they're in the same homology class, right? So, all right. So let's say, so let's suppose there is another choice of beta, say beta 0, and let gamma 0, right, be the unique element of UP minus 1, such that, yeah, so it's unique because it's like, you know, again, it's like this phi is injective, right? So there's a uniqueness there. Such that, yep, phi of gamma 0 is equal to V of beta 0. Okay. So that's where we're at, right? We have beta and beta 0, we have V beta and V beta 0, gamma and gamma 0. Okay. So what do we know, right? We know that phi of beta is equal to phi of beta 0 is equal to alpha. Okay, and again, it's like we're going to look at what happens. It's like when you just have Z2 coefficients. So you know that when you have Z2 coefficients, right, and you have things which are the same, if you add two of the same thing together, they go to 0. So what that means is that phi of beta plus beta 0, of course, is just 2 alpha, which is 0. Okay. So that means that phi, well, that means beta plus beta 0 is in the kernel of phi, but you have exactness, right? So this is in the image of psi. Okay. Okay, so it's in the image, so that means there exists something here. Let's call that mu. Okay, so beta plus beta 0 is in the kernel, it's like of psi, so it has to be an image of phi. So it exists, it's like, so it implies that there exists something, let's call that mu, in UP, okay, with the property that phi of mu is equal to beta plus beta 0. Okay, all right, so now that is block number 2. And of course, as you might expect, we're going to use the fact that this diagram commutes. Okay, so since this block commutes, right, if I take first the boundary and then the phi of it, so phi of the boundary of mu, right, is equal to the just the boundary of beta plus beta 0, actually, I'm sorry. No, that's not what I wanted, right? Okay, so V of beta plus beta 0 but v of beta and v of beta at 0, it's like are coming from a gamma and gamma 0. Okay, so okay. Okay. But then we use the fact that we have injectivity of phi. So this means that u of mu is equal to gamma plus gamma 0. Okay, so this is what you want, because that means gamma and gamma 0 differ by something which is the boundary. Which means that they generate the same homology class. Okay, all right, so right, so that shows that your choice, I mean, it's like up to homology, it's like I mean, it's like the map, shall you say, this connecting homomorphism up to homology is independent of the choice of beta. Okay? All right. So the final step is to show the independence with respect to alpha. Okay. So this is step 4. Independence of the choice of alpha. Okay. So as before, it's like we're going to assume that there are two possible alphas, right? We're going to say consider a different choice of alpha, say alpha 0. Okay, so I'm just going to leave this here and then say that there's an alpha and alpha 0 here. Okay, so you let beta 0 and gamma 0 be the corresponding things you get as before. Sort of be defined from alpha 0, right? The same way that you derived sort of beta and gamma, it's like from alpha, right? So there's a beta 0, and then there's a gamma 0, and there's a v beta 0 here. Right? Okay, so there you have the usual diagrams. Okay. So since alpha and alpha 0 represent the same homology class, right? That means that they differ by a boundary. So there has to be some thing in WP plus 1, it's like whose boundary it's like is the difference of alpha and alpha 0. So let's call that nu. Okay, so that means there exists nu in WP plus 1 such that W of nu is equal to alpha plus alpha 0. Okay, so alpha and alpha 0 differ by something in the boundary. Okay, and the point is that now this psi is surjective, right? There's a way to find something that's like which maps to nu, right? There exists a row which is now VP plus 1 such that psi of rho is equal to nu. Okay, then that diagram is the third box here. Right, so this is box 3. So by commutativity, box 3, right, what has to happen is that they both have to map, it's like to alpha plus alpha 0, right? V rho and beta plus beta 0, right, both map by psi to alpha plus alpha 0, right? So if I add the two of them together, so this implies that V rho plus beta 0 is in the kernel of this map, right? Which is the image of phi, right? Kernel of psi is in the image of phi because, again, exactness at this point here. Which means that there's something here, let's call that mu prime, right, in UP, right, which maps to this sum. So there exists a mu prime in UP, right, with the property that its image under phi is equal to V of rho plus beta 0. Okay. All right. So now we're going to use commutativity of this block here. So by commutativity of the second block, right? And the fact that, again, it's like, you know, the boundary squared is equal to 0. Right, so that means that Okay, so I should draw it this way. U prime maps to V rho plus beta 0. This maps, so this maps to 0, right? So you just have V of beta plus beta 0. Okay, and then this, okay, so but then this is injective, right? So this has to come from gamma plus gamma 0. Okay. All right, and then this is the U map. And okay, so we know that this combination, right, of mu prime is V beta plus beta 0, right? But because of injectivity, right, this means that U of mu prime is equal to gamma plus gamma 0, right? Which is exactly what you want as before. That means gamma and gamma prime differ by something which is in the boundary, right? So gamma prime, sorry, gamma 0, right, differ by a boundary. So they represent the same homology class as before, right? And so this shows that our construction for the commuting homomorphism, the connecting homomorphism is well defined, right? Right. So that's basically what we wanted to show. So I should say that we haven't actually showed that the in sort of the induced maps, it's like a homology which come from the inclusion and projection maps, right? Sorry, not inclusion and projection maps, but the it's like the chain maps together with the connecting homomorphism, right? Actually gives you this long exact sequence, right? You have candidate maps, you still have to show that it's like that sequence actually is exact at every point. And again, it's like the part that's like one has to show, it's like which requires a little bit of work potentially, is the one which involves the connecting homomorphisms. So we're not going to show that, but again, at least you now have a candidate, it's like connecting homomorphism to show or to sort of verify that you have exactness. Okay, so let me just stop here for now.